The final section of coverage in week 3 is section 5.2, the binomial probability distribution. We've already previewed it. I've introduced you to it in the last example. Remember when we were flipping a coin? We flipped 15 coins, and we were curious about how many heads we might expect. So this distribution counts the number of heads. And that's the exact purpose or description of what the binomial distribution is for. My abstract description of the binomial distribution is the following. When we try a two-way outcome, success or failure, several times, how many successes will we get? So remember, bi is the prefix for two, and this is called binomial because we are performing an experiment that only has two possible outcomes. There are many, many instances where this might occur. Heads or tails, 0 or 1, boy or girl, win or lose, success or failure are the abstract terms for any of those. So I'm sure that you can think of many other applications where something can only occur in two ways. When I get to the parking lot, will my favorite parking spot be available or full? That's just one other silly example. Or when I go to McDonald's, will their ice cream machine work or not work? It seems that their soft serve machines are always broken down. So I might be interested in asking a question like, if 80% of the McDonald's have a soft serve machine that is broken down, then if I try the 10 McDonald's in my county, how many of them will have an ice cream machine that works today? That's the classic formulation of a binomial problem. We want to find out how many successes we're going to get. I have a really cool illustration for this. We're going to take a look in just a moment at what's called the virtual Galton board to see how a binomial distribution can be simulated by dropping a whole bunch of balls down a peg board. It's really cool. As far as a little bit of context for this class, you will not be tested heavily on the binomial distribution. There are really only a couple of questions in the course that relate to it directly. I was kind of surprised by that when I started teaching this class, because in a normal stats class, this topic gets pretty heavy. There are formulas for the number of successes. There are formulas for the mean and the standard deviation. There are tables that you can use to look up. But none of that is tested in this class. There is a little bit that's tested, and we'll go over that below. However, the binomial distribution is a natural lead-in to the normal distribution. And that is going to be a very foundational topic in this course. So I think that there are a lot of qualities of the binomial distribution that are just really important for us to see, to give us a little bit of this context when we move on to the normal. All right, so let's take a look at this virtual Galton board. I searched around a little bit and found that I like this website the best. And I'm going to restart this one. Give me a second here to turn the knob. Okay, so I'm starting this video out very small and very slow. What we have here is a peg. We're kind of looking at an end on, it's a peg on a board. And we are dropping ping pong balls onto the peg, and each ping pong ball may bounce either to the left or to the right. So let's just suppose that bouncing to the right means heads or success, and bouncing to the left means tails or failure. So here's a ball. This one just dropped down, and it looks like it's turning out to be a success. It's a head. Here's another ball. Oh, that one's also going to the right. Now there are 5 heads. Here's another falling ball. That one's going to be tails. So now we're going to have 4 tails and 5 heads. So what we're doing here is called a trial. Each peg represents a trial. It only has 2 possible outcomes, left or right, failure or success. And I have adjusted this slider so that the probability of bouncing to the left is 50% and the probability of bouncing to the right is 50%. We're going to parameterize these numbers and make them into variables for this course. So let's keep track of this. We've got a size, number of pegs, number of trials. That's what we call lowercase n. The probability of a success, the probability of bouncing to the right, is called P. And the probability of a failure, the probability of bouncing to the left, is Q. So if we go back to the lecture notes here, I've written that down. N counts the number of trials, which is going to be represented by the rows of pegs. And the example that we're looking at now, N is only 1. P is the probability of successes, Q is the probability of failure, and X will be our variable, which will be the number of successes. And that's going to basically end up counting the number of right bounces. Each falling ball represents a sample of N trials. That'll make sense when we start increasing the peg board. There are a few requirements which you will be tested on. N must be fixed. Okay, so there must be a fixed number of trials. So in the example that I gave a minute ago, if we go to 10 McDonald's, how many of them will have an ice cream machine that works? So in that case, N, 10, is going to be fixed because there are only 10 McDonald's in that county. P, the probability of success must be the same for every trial. So it wouldn't work if there was one McDonald's franchise that had a better ice cream machine than the others. We have to assume that they all had the same probability of breaking down. Of course, coins are like that. Every time you flip a coin, you have a 50% probability of a head. And the final requirement is that the trials must be independent of each other. And again, flipping coins, every coin is independent of every other coin. And we would assume that whether the ice cream machine works in that city is probably going to be independent of whether the other ice cream machine works in the other city. They don't affect each other, right? Okay, let's start playing around a little bit more with this distribution. But what we're getting here is a histogram. If we try flipping many coins, so far we've flipped 21 coins. There's 22. And we find that 10 of them have been tails and 12 have been heads. Tails here again represents, this axis down here is counting the number of heads. So either some of them have turned up 0 heads and some of them have turned up 1 head. And as you can expect, if we try this many times, that these probabilities should get really close to 50-50. So let's speed this up a bit. Let's speed it up a lot. Flipping more and more coins, and the law of large numbers tells us that the more we flip, the closer this probability should get to 50%. This one seems to kind of favor tails, doesn't it? All right, well, that's remember, statistics is never exactly perfectly theoretical. Okay, let's take this up to two coins, and I'll make it slow again because I want to illustrate how to visualize this on the pegboard. Okay, so what we're going to see now is 2 rows of pegs. The first row represents the first coin. That one was tails. And then the second row represents the second coin. Oh, that one was also tails. So this coin is heads, tails. And this one here is heads, tails. And this one is also going heads and then heads. So this one got 2 heads, see? So what we're going to get here is a histogram. When we flip 2 coins, we can either get 0 heads, 1 head, or 2 heads. So each one of these falling balls now represents an experiment with 2 flips in it, 2 coin flips. It's a sample of size 2. So the question is, if we pile all those samples up, how will they fall? So let's speed this one up and see how it ends up falling. And we should let this number get up into the hundreds, really, to give us an accurate picture. Well, I think the picture is starting to form. Let's just go ahead and pause it there. So you would basically expect that the coins, the samples with 1 head would be the most common. Does that make sense? If you flip 2 coins, you'd probably expect one of them to be heads, right? And you can see almost exactly here that this ratio is 1 to 2 to 1. So for every time we get 0 heads, we get another sample with 2 heads. They're equally likely, but getting 1 head is twice as likely. And we can increase this experiment as much as we want. We could try flipping 3 coins. Let's see if we can take it up to 15, which was the graph that we got before. Oh, so close. We can go up to 14. Okay. All right, so now we're flipping 14 coins. Each one of these balls represents a sample of 14 coins. And down here, we're keeping track of how many of them turn up 0 heads, 1 head, 2 heads, ... with a maximum of 14 heads. What kind of a shape do you think we're going to get? Well, I'll bet you can guess that we're going to expect a shape a lot like this one. All right, so believe it or not, I actually paused and let this go to 1,000 trials, or 1,000 samples, I should say. 1,000 samples of 14 trials each. And this is how the distribution turned out. As you can see, it is quite a nice bell-shaped curve. I just want to